So am I audible? Muthukumar, am I audible?
Yes.
Okay, thank you. Okay, so let's wait for 1 or 2 more minutes, then we will start. You can see my screen, right?
Yes.
Okay, thank you. So okay, so we will solve today practice 7 assignment and then do some other thing, like if you need some help in some theory of like this course introduction to rings and fields consists of 2 parts, rings and fields. So basically the rings part was done up to week 6 lectures and fields after that. So week 7 practice assignment consists of questions of field section. So let's start this practice assignment, week 7 practice assignment. Up to week 6 practice assignment, I have done these all these practice assignment in past interaction session, like first, second, third, and fourth interaction session. So we will today do this one, 7th practice assignment. So let's start. Okay. It's freezed. What is the question? C be the field of complex number. Field of complex number, and Q be the field of rational number. Let alpha belong to C, B root of x to the power 8 minus 1. Which of the following are possible degree of alpha over Q? Which of the following are possible degree of alpha over Q? So let me, okay, I should ask you, what is the definition of field? So do you know definition of field? Anyone can answer.
So field is a ring.
Yeah.
Ring means commutative ring with identity.
Okay.
In which every non-zero element has multiplicative inverse.
Every non-zero element has
Multiplicative inverse.
Okay, fine. This is the definition of field. So now what is the meaning of saying that degree of a element? Like, so do you know meaning of this? Alpha belong to CB, an element of so alpha is a complex number. So you are saying that degree of alpha over rationals. What is the meaning of this? Do you know?
Degree of the minimal polynomial over Q satisfied by alpha.
Okay, right. Degree of the minimal polynomial for alpha over Q, right? So what is the so here given that alpha is the root of this x to the power 8 minus 1. So what is the possible degree of alpha he is asking to us? So can you guess or you have any intuition what can be possible degrees? So given options are 1, 2, 6, 8. Okay. Monic, the minimal polynomial is irreducible polynomial. If it is reducible, then you can also reduce it. So minimal means least. So it is irreducible monic polynomial. So is x to the power 8 minus 1 irreducible or not?
X power 8 minus 1 is?
Irreducible or not? Question.
It is irreducible.
Okay. You are saying, Muthu Kumar is saying x to the power 8 minus 1 is irreducible. Okay. So let me give you its factorization. So you are correct. Not correct. So what is its factorization? You can write x to the power 8 minus 1 as x to the power 4 chi square minus 1 square. So a square minus b square you can apply here.
Sorry, it is reducible, right?
Yeah, it is reducible. So yeah. So what are the possible degree? Now you can see, right? What are the possible degree? Now you can further factorize this as yeah. How you will factorize this? X square minus 1, x square plus 1. And factorize this one also. This is also not irreducible, right? X to the power 4 plus 1 is not irreducible. So factorize this one also. Yeah. So what are the possible degrees of an element? Okay. Suppose alpha is root of this x to the power 8 minus 1. What can be least degree monic polynomial? Then alpha should be root of one of these three polynomials, right? Either x square minus 1 or x square plus 1 or x to the power 4 plus 1, right? Muthu Kumar, you agree with me or not?
Given that x squared minus 1, you can factorize.
Yeah. Yeah, we can further reduce this. Right. Yeah, you can further reduce it. So you can write is x minus 1, x plus 1, x square plus 1, and x to the power 4 plus 1. And now you can check that all these are irreducible. So now the question arises, if alpha belongs to C is a root of this polynomial x to the power 8 minus 1, then alpha must be root of one of these polynomial, either x minus 1 or x plus 1 or x square plus 1 or x to the power 4 plus 1. So what are the possible degree of alpha over Q? Now you can see, right?
1, 2, 4.
Yeah. So given option are 1 and 2. So 1 and 2 are there. So let me write justification. Since alpha belongs to C is root of x to the power 8 minus 1, this implies alpha is root of one of the irreducible polynomials x minus 1 comma x plus 1 comma x square plus 1 comma x to the power 4 plus 1. This implies possible degree of alpha is 1 to 4. Okay. This implies A comma B are correct. So now next question. Okay, second question. Choose all correct statements. What happening?
Excuse me.
Yeah.
In the previous problem,
Yeah.
1 or 2,
Yeah.
maybe 1 only or maybe 2 only. How do
Yeah.
we say that 1 as well as 2 both are possible?
This depend upon the choice of alpha, right? Suppose you are taking the polynomial, so let's take the polynomial x square minus 1 instead of x to the power 8 minus 1. Then depend on the choice of the root. If you take root 1, then it is just a root of the polynomial x minus 1. Suppose you can, okay, let me explain this one.
Or possibly,
Yeah, let me explain, but this screen is freezed. I don't know what happened.
okay, the question they have asked, possible degree of alpha, right?
Yeah, possible degree of alpha. That's what I am explaining. Suppose the polynomial you take x to the power 4 minus 1, because 8 is too much higher, so you can work with 4, right? So x to the power 4 minus 1, then its possible roots are 1 minus 1 iota minus iota. Then you can see that its factorization is x plus 1, x minus 1, and x square plus 1. Then you can see that it's, if you take element 1, it's the root of x to the power 4 minus 1, it's root 1, then its degree is 1, minus 1 its degree is 1, iota its degree is 2, minus iota its degree is 2. So that's what here happening. So x to the power 8 minus 1, then alpha is any arbitrary root, so we cannot say explicitly its degree, but its a possible degree is only 1 to 4. Agreed or not?
Okay.
But this screen is freezed. I don't know what happened to this. This is not even working. I hope this will work now. This is not working. Let me cut it and start again. Oh. Wait for a minute. Ah. To this. It is not working. I'm facing issue. That's let me leave and join again.
Coming here, you know.
This is freezed completely. I don't know what happened. Just wait for 2 minutes. I'm restarting this device again. This book will restart. Okay. Okay. You can hear me, right? Mutkumar, you are host. Can you please make me host? Muthukumar.
Hello.
Yeah, just go to participants and make me host, because otherwise I cannot share my screen. Because you become the host when I leave the meeting. So just make me host. Just click on my name, Prakash Joshi, and make me host. There will be an option, make to host.
Okay. Prakash Joshi asked to start video chat. Make host.
Yeah, make host.
Okay.
Thank you. This starts. Yeah, we are doing here. So we are doing the second question of this assignment. So let's start. So Q be the field of rational numbers and pi is a transcendental number over Q. Okay. So choose all correct. Okay. Now this will work. Choose all correct statements. Of rational numbers and phi is transcendental over Q. What is a transcendental number? Do you know? Phi is transcendental over Q. So what these are the following options. A is equals to Q root 2 does not equals to Q root 2. So what is a transcendental number? Do you know?
Which is not an algebraic number.
So what is algebraic number?
Algebraic number, that numbers is a root of an equation with coefficients in Q.
Yeah, root of a polynomial equation with coefficient in. So pi is a transcendental number. This is a hard exercise. You will prove this in your first course in maybe you will do it somewhere. So but it is given to us that pi is a transcendental number. So we have to prove. First statement is saying that Q square root of 2, like square bracket, is not equals to Q curly this bracket, round bracket, square root 2. So how you will, is this true, or do you know the notations? What is Q root 2? Okay, let me explain you notation what your structure done. So Qx to C, there is a morphism sending everything fx belongs to Qx to f evaluated at root 2. So now he is saying this subring, let's name this morphism phi. He is saying this image phi is a subring of C, subring of C denoted as Q square bracket root 2. And what is Q this round bracket root 2 and Q round bracket root 2? Smallest field containing
Q and root 2.
yeah Q and root 2. So these two are notation. So how what you can say that Q is this square bracket and round bracket, are they same or not same? Is this true or false?
It is true.
You are saying true. So how you will argue?
Root 2 is in Q of ordinary bracket 2.
So how
Root
you will
2.
argue that?
Root 2 is not an element of square bracket.
Root 2 is not an element of square bracket. Why it is not element? It is element, right?
Because from the map.
Okay. So is fx equals to x a polynomial there in Qx? X
Yes.
is, yeah. So when you will send it to f root 2, it will be root 2, right? So Muthukumar is saying, this is said by Muthukumar. Muthukumar, which is not correct. Tell me. Is this true or not? What do you think? Try to do something. How you will argue? Just think about this map phi. If you can prove this Q square bracket root 2 is filled, then it is smallest field, because it will be obviously Q round bracket root 2 is a smallest field. So that field is contained in Q root 2 always. But this field is smallest than in that case. So then both should be same, right? If you can prove it somehow that the image of phi is a field itself. So how you will prove this? Are you getting some idea? Okay. If not, then let me say. So you know C is a field. Since C is a field, this implies image phi is an integral domain, right? Now, what about kernel phi? Kernel phi consists of all those polynomial fx belongs to qx such that phi may f of root 2 is equals to 0, right? Now, since q is a field, then qx is PID. Agreed or not? Muthukumar, do you know this fact? Q is field, then qx is PID.
Right.
Yeah.
Okay,
So,
every field has only two maximal ideals.
yeah, field is PID itself. Then if field is, suppose Q is a field, then polynomial ring over this is a PID in one variable. Even ED, Euclidean domain. Do you know this fact or not?
We know.
No or don't know? Basically, it is not a hard fact because you can see in Q there is only one polynomial of the form like 0. 0 is like there is only one ideal 0. So here the ideal possible are only means like x polynomial like x square and these forms. So basically every ideal here will be principal ideal. You can argue by some. Okay. So since here I should write this fact, since Q is filled, this implies Qx is PID. This implies kernel phi is generated by single polynomial say f. What this implies? This implies kernel phi is equals to ideal generated by f. So now by first isomorphism theorem, first isomorphism theorem, qx mod kernel phi qx mod is isomorphic to image phi, but we know this is an integral domain, and this is ideal generated by this element f. Now see, kernel image phi is an integral domain. That means this should be prime ideal, right? That means this is a prime ideal. But in PID, every non-zero prime ideal is maximum. So only need to show kernel phi is non-zero. Muthukumar, how we will argue that kernel phi is non-zero? Now it is almost obvious. Jennifer Princey, do you have any idea how we will argue now? Kernel phi is non-zero.
True. Is in kernel phi.
Yeah. How we will argue that kernel phi is non-zero?
Polynomial x squared minus 2.
Yeah, correct. So since x square minus 2 belongs to qx and f equals to, it's like g equals to x square minus 2 and g root 2 equals to 0. This implies kernel g belongs to kernel phi. 0 does not equals to g. This implies kernel phi non-zero. This implies kernel phi is a maximal ideal. Is maximal ideal. What this implies? This implies qx mod kernel phi, which is isomorphic to image phi, which is equals to q, this is square bracket root 2. This is now filled because kernel phi is a maximal ideal. So this implies this is also filled. This implies q root 2 is a field. Now we know q square, since we know q square root 2 is smallest field smallest among all fields containing q and root 2. So this should be smaller than this one always. But now See, this one is always, since we know this q root 2 is the smallest field, so this should be contained in this one because this is also field. But q root 2 is always contained in q this one bracket 2. This implies q root 2 is equals to, let me, always this implies q root 2 is equals to, this implies, okay, is this clear or not? Do you have anywhere doubt or something? You can ask me. Is this clear?
It is clear. Whether
Yeah.
it is valid if root 2 is replaced with any other irrational number.
Any irrational number is not valid. Suppose you replace it by pi.
Root 5.
Sorry, pi. Transcendental number pi. Then kernel phi is 0, right? Because there is no polynomial over qx which have root as a pi. That's why pi is transcendental, right? Agreed or not? Yeah. So kernel will be, yeah. So in that case, you cannot argue in this.
But root pi is not.
Root 5 is a algebraic. Root 5 is a algebraic number. So you can argue in similar way for root 5. For any algebraic number, this statement is true. I prove that. This is proof for any algebraic number. Instead of root 2, you can replace it by any algebraic number. Then it is true statement.
Algebraic over Q.
Yeah. Whenever I am saying algebraic number, it means algebraic over Q. So is this proof clear or not?
Clear.
Okay. There is other participant. Jennifer, is this clear or not?
Yes, sir.
Okay. So now the second option says now this is interesting. Is this clear or not? Is this equal or not? Q square bracket pi and Q round bracket pi. Is this same or not? Okay, first let me ask you a question. Each Q pi filled? This is the first question for you. So tell me, is this filled? Jennifer, is this filled?
No,
Why? Why it will be not filled?
pi is a transcendental number.
So why? So what? Pi is transcendental number. So what? So what?
The kernel pi is singleton 0.
Okay, so what? You define phi map from here to here. Qx.
So therefore, Q pi become only integral domain and not it is a field.
How you will argue? How you can say that it is not filled? It says that it is integral domain, but how you are saying it is not filled? You have some rigorous proof, right? How you will argue that? If you are saying it is not filled, give me an element which is not unit, non-zero element which is not unit here, right? Kernel phi
Pi is
f x belongs to x such that f of pi is equals to 0. This is precisely 0 polynomial. So what? So by first isomorphism theorem, qx mod over kernel phi is isomorphic to image phi, which is defined as q square bracket pi. Now this is an integral domain. Now see, this is qx over 0 ideal, which is isomorphic to qx. So this implies q pi is isomorphic to qx. So now each qx field is this field. Tell me, Muthukumar, is this field? Polynomial ring in one variable over q. It is easy. You should just say yes or no. Is this field or not?
Q square bracket x.
Yeah. Q polynomial ring in one variable over q. Is this field? What is the inverse for any? I prove you precisely all the units over this ring. If K is any integral domain, I prove that all the units are just the units of that integral domain in my first interaction session in polynomial ring over one variable or any number of variables. Do you remember that?
So Q is a field, and therefore Qx is also a field.
Qx also a field. How? Give me inverse for the element x. What is the inverse for x?
X is there.
So what is the inverse for x?
So it has no inverse.
So how you are saying it is field? Jennifer, is this field or not?
Field, sir.
Yeah.
True.
Okay. Why? Why it is field? You should unmute yourself. Otherwise, you will get nothing from my session, right? You should unmute yourself and talk with me. That's how I can understand what you are understanding or not. So you should unmute yourself. So if this is a field, then you have inverse of every element, right?
Yes.
So I am giving you an element x in polynomial ring qx. So what is the inverse for this element x? In first interaction session, I proved this exercise precisely. Let me write here. In first interaction session, we prove that if R is an integral domain, then the only unit of polynomial ring Rx are units of R. Now so only units of qx units of Q means all the units are the units are non-zero in Q. Okay. So any non-zero, non-constant okay, non-zero, non-constant polynomial does not have inverse. This implies Qx is not filled. This implies Qx isomorphic to Q pi is not filled. This implies Q curly bracket pi is not equal to Q. So is this clear or not?
One is a field, the other one is not a field, therefore they cannot be equal.
Yeah, they cannot be same. So why they cannot be same? Can you confirm me? I just want to understand that. Did you get this proof or not? One is filled, other is not filled. So what? So why they cannot be same? Muthu Kumar.
For equal, both must be of same structure, both must be filled.
So can you give me an element in Q in one which is not in other? Then it will be more clear for me, right? Under this isomorphism, where I prove that Q pi is isomorphic to Qx, and I give you element not unit here, right? X is not unit here, and X goes to pi here in this isomorphism. So pi is not unit here in Q pi. But you can see in this ring, pi is unit. Precisely the inverse is 1 over pi. But here 1 over pi is not the element. Agreed or not?
Agreed.
Yeah. So this is the idea.
So Q pi.
Yeah.
Q of pi.
Yeah. So this is the idea that one is filled and other is not. Here is you have inverse of pi, but here you have inverse of pi, but here you don't have any inverse of pi. So both are not same. Now third option is okay. For some real number alpha, then Q alpha plus 1 is equals to Q plus 1. Okay, tell me, is this true or not? Jennifer, is this true or not?
True, sir.
Yeah.
Yes.
Can you say again?
True, sir.
True. So what is the argument?
So, Alpha is a real number, and if the conditions was given that 2 of square bracket alpha is equal to 2 of alpha, where
Yeah.
alpha is a real number, then alpha plus 1 also a real number.
So what? Is pi not a real number? Pi is also real number, right? But for pi, I proved that both these are not same. So what?
See, what is given q square bracket alpha is equal to q of ordinary bracket alpha for
Yeah.
every real number alpha.
Okay.
Therefore, alpha
For
plus
every
one-
real number not, for some real number alpha. For every you cannot prove. I gave you some counter example pi, right? Pi is a real number, but I proved that q pi is not same as q round bracket pi. So for some real number alpha it is given, like root 2, I proved that q root 2 is same as q square bracket root 2. So tell me, how you will conclude from first one that then q alpha plus 1 should be same as q square bracket alpha. Tell me, Muthu Kumar, you are saying something, right?
valid only for some real alpha.
Yeah, for some real number alpha they are valid. Even I gave you some hint that for what kind of real number it is valid. Okay, let me ask a question. And you should answer this one by first part, A part. For what real numbers
It should be an algebraic number.
alpha? Yeah. Okay. For what number? Okay. What is the answer?
For
Muthu
every
Kumar,
for every algebraic number, it is true.
yeah, algebraic number it is true. And is this true only for algebraic number? For every algebraic number it is true. But is this true for only algebraic number? Can it be true for any transcendental number?
Because in that case, your kernel pi will become singleton 0.
So what? Okay. Now next question for you. Can q alpha is equals to q alpha for transcendental number? Alpha, tell me. I gave you one example of transcendental number. If alpha is equals to pi, then I prove that q alpha cannot be same as q round bracket alpha. So can you mimic the same proof for any transcendental number? What is specific about pi I use here? Can I use any? Did I use any specific property of pi here? I just use that it is a transcendental number, so kernel is 0.
So it is true for every transcendental number.
So yeah. So yeah. By part B, q alpha does not equals to q alpha for any transcendental number alpha. Okay. So now tell me, what is this statement saying? Precisely saying that if alpha is any algebraic number, then alpha plus 1, q alpha plus 1 is same as q square bracket alpha plus 1. So the question reduces to you to prove that is okay. Now the question, if alpha is algebraic number, is alpha belongs to R, is algebraic number, is alpha plus 1 also algebraic number? Belongs to R, is also algebraic number. Can you argue for this? Is this true or not?
So you can assume alpha is algebraic number.
Okay, so alpha is algebraic number. So what?
So it satisfies a polynomial.
So So yeah, so this, let's assume alpha is algebraic number. This implies it satisfies, this implies there exists fx belongs to qx such that f alpha equals to 0. Then what?
F of x minus 1 will satisfy that alpha plus 1.
Then you are saying that f of x minus 1, this one, this polynomial,
This polynomial will be satisfied by alpha plus 1.
x minus 1, yeah, correct, alpha plus 1, yeah. And let's check how you will say. Let's, the polynomial is given to you is x square, let fx is equals to x square plus 1. Then you are saying iota plus 1 is root of x minus 1 ka whole square plus 1, which is x square plus 1 minus 2x plus 1, which is x square plus, yeah, it is correct, x square plus 1 minus 2x, x square plus 2 minus 2x. So yeah, it is correct. Okay, so this is also a good idea, but yeah, because how we are guessing this thing, is this clear to Jennifer, whatever the name, I am forgetting the name, is this clear to you?
Yes, sir.
How it is clear, tell me. What argument Muthukumar gave, is this clear to you or not?
Taking a polynomial f of x is equal to x square at plus 1 and just expanding and
So tell me how this alpha plus 1 will be root of this polynomial, what Muthukumar claiming.
But if we substitute here in f of x minus
Yeah,
1, it's equal to
agreed,
alpha plus 1.
yeah, agreed, but I just want to hear from her. Okay, so this implies fx minus 1 has alpha plus 1 as a root okay, minus 1 belongs to qx. This implies alpha plus 1 is algebraic. So now I conclude that if alpha is algebraic, then alpha plus 1 is algebraic. So now what you can say?
Therefore, q of alpha plus 1 is equal to q of square bracket alpha.
Yeah, this implies q of alpha plus 1 is equals to q of alpha plus 1. Okay, now let me ask you another question from here. So here he gave you 1, I am giving you question. Given alpha algebraic number and beta any other algebraic number, is alpha plus beta also algebraic number? More precisely, I want to ask that is q alpha plus beta? He just asked you in the case of beta equals to 1. I am asking you general version for that question. So what is the idea? Muthukumar, now how you will generalize your polynomial? In that case, you just tell that this is the polynomial. So now how you will generalize?
So both alpha and beta are algebraic.
Yeah.
So therefore, there exists polynomials fx.
Okay. And gx, right? Jennifer, do you have any idea how is this true or not? Jennifer.
No, sir.
Okay. Muthuma, do you have any idea how we will prove such kind of argument?
So we will have to.
What your intuition says, first tell me, is this true or not?
I think it is not true.
Why it is not true? You prove it for beta equals 1, right?
Alpha plus 1.
Yeah, when beta is 1, you prove that alpha plus 1 is algebraic number. I am just asking for any algebraic number beta. Okay, let me tell you something. Proof. Given alpha and beta are algebraic numbers, this implies there exist minimal polynomials f comma g belongs to qx for alpha and beta respectively. Let's suppose degree of f equals to m, degree of g is equals to n. Now since f and g are minimal polynomials, so they are irreducible. So now I am saying that, talking about this extension, q of alpha comma beta over q. Yeah. Q alpha over q and then q alpha beta over right. This should be less than equals to this one. So what? So what we can conclude from here? Now this degree, so this is same as q alpha beta over q alpha, and this is q alpha. What I'm doing? Q alpha over q. Now see, this is equals to m, and this is less than or equals to n. So you can see this implies q of alpha comma beta over q is less than mn. Means there is a polynomial you are getting, means this is a finite extension, right? This means q alpha comma beta is finite extension. This means every finite extension is algebraic extension. So this means if there is any field containing alpha, what is the meaning of q alpha beta? Smallest field containing q alpha and beta. So now if any field contains alpha and beta, then it must contain alpha plus beta. Agreed or not? Muthukumar, agreed or not?
Agreed.
So this means since this extension is algebraic extension, that means there is a polynomial h which in Q, since this extension is algebraic extension, since extension is algebraic, this implies there exists h such that h belongs to Qx such that h of alpha plus beta is 0. That means alpha plus beta is algebraic over Q. Okay, so I proved that alpha plus beta is algebraic. This means that Q alpha plus beta is equals to Q of alpha plus beta. So I prove a general version of UX for all algebraic numbers alpha and beta. Okay, is this clear or not? Muthukumar, is this clear?
It is clear. The
Jennifer,
result is clear, but anyway, the proof is somewhat complicated.
yeah, is the means if there is any doubt you can ask me in proof.
Okay.
Jennifer, is this clear or not?
Yes, sir.
Do you have any doubt or something?
Sir, whether can we conclude that sum of two algebraic numbers are algebraic? Can
Yeah.
we conclude this?
Yeah, this is the proof I gave you. Sum of two algebraic number is an algebraic number. I gave you a proof for this.
Okay, sir.
Okay. But it's a good exercise to do if you are interested in mathematics. Is sum of two transcendental number is a transcendental number. So try to do. If you get a proof, or tell me also. Is product of two transcendental number? You can also prove in similar manner. Product of two algebraic number is an algebraic number. But try to prove is the product of two transcendental number is a transcendental number or not. So these are some interesting questions. You should try.
Okay.
Muthukumar, is sum of two transcendental number transcendental or not?
Pi and 1 minus pi.
Yeah. How you will argue 1 minus pi is transcendental number?
Because if 1 minus pi satisfies some equation,
Okay. Then what?
then pi also satisfies the equation.
Okay. You will
Some slight modification.
Yeah, you will claim that pi will satisfy this 1 plus x equation, right? F of 1 plus x.
Yes.
Yeah. So, okay. Then you will claim that sum of two transcendental number need not be transcendental.
Yes.
That is great. But can you say something more when it can be transcendental? Is sum of e and pi is transcendental or not? Suppose e is, in this case, you take a nice case like there is something cancellation going on. That's how you argue. Like you prove that sum of two transcendental number is algebraic number in that case. Because 0 is algebraic number. But what you can say, like 1 is algebraic number. But what you can say, like e and pi, both are transcendental. Can you say something in that direction? These are some open questions. So let me go ahead. Let K over F be any field extension. the set of elements in K which are algebraic over F each forms a subfield of K. This is slightly generalization of part C exercise, nothing more than. I proved that in case of Q, this is slightly generalization in case of any arbitrary field. So Muthukumar, is this true or not?
I think it is true.
Okay, how you will prove? Justification. How you will justify yourself? Suppose K over F be any field extension, the set of elements which are algebraic over F. Let's denote this by L. Okay. Subfield of K. How you will prove this one is a subfield of K? You need
What
to
we have
prove,
proved?
for proving something is subfield. How what you need to show that product is there, sum is there, and you need like one is there, zero element is there, inverse is there for any. Okay. So how you will prove? Okay. So let alpha comma beta belongs to K. Be algebraic numbers, algebraic over F. Then we need to prove to show alpha plus beta is also algebraic. But how we will do this? Is this clear or not? How we will do this? If clear, then tell me how we will do this. Because I done same calculation in part C.
With Q, we have done this one.
Yeah. So generalize this for any arbitrary field. Just replace Q by alpha in that calculation. See, you are not doing seriously these things. This extension, take this extension. This is this extension degree is
Okay,
F.
the same thing with Q replaced with F, we can prove it. Okay,
Yeah,
no
yeah,
problem.
yeah,
We can assume that
yeah,
finite dimensional, therefore this algebraic extension is
yeah,
okay.
yeah. You can. This one is less than Mn. So finite extension. This implies algebraic extension. Algebraic extension. This implies since alpha plus beta belongs to F alpha beta, this implies alpha plus beta is also algebraic over F. Now what about alpha beta? Is alpha beta belong to this field F alpha beta? Alpha comma beta? Let me write. Is this belongs to this, true or not? Jennifer, is this true or not?
True, sir.
How? How?
It's finite field
Yeah.
extension.
So what? Finite field extension. So what? If alpha and beta are any two element of any field, then is there product in that field? The question is this. What is the property of field? Do you know definition of field?
We have proved only the closure property with respect to addition.
Yeah. Now I am asking to multiplication.
Yes.
Jennifer, Unmute yourself, otherwise you will not get anything.
Multiplicative inverse will be there.
No, first tell me multiplicatively how you will prove it is multiplicatively closed. If alpha is any algebraic number, beta is any algebraic number, I need to show that alpha beta is there, also algebraic number, algebraic over F. So how you will prove this? This I have done already. You just need to say me alpha. I am just asking you that is alpha beta belongs to this field F alpha comma beta. F alpha comma beta is the smallest field containing alpha and beta. So this field contains alpha and also beta. So if any field contains alpha and beta, then this contain also their product or not? Tell me.
It is a field, therefore product is also there.
Yeah. So that's what I want to hear from you, but you are not even that much confidence. So try to speak in class, otherwise you will not get. That's what I want from you. You should interrupt me, ask me your doubts. Alpha beta belongs to F alpha beta. So this implies alpha beta is also algebraic over F. So now what? Other thing, alpha inverse belongs to alpha alpha comma beta. Is this true or not, Jennifer?
Yes, sir.
How this is true?
Alpha is algebraic number and alpha is also algebraic number.
How you will prove this is algebraic number, alpha inverse?
F of alpha beta is a field, and
So,
alpha is in that field, and if it is non-zero, then its inverse exists.
Yeah. That means, yeah, we have to assume there. Let's assume. So let 0 does not equal to alpha. This means alpha inverse belongs to F alpha beta. This means alpha inverse is also algebraic over F. 1 belongs to F alpha comma beta. This implies 1 is always algebraic over F. So I have proved all properties, right? Is anything remaining? I proved inverse. 0 is obviously there. Yeah, let's write 0 also there. 0 belongs to F alpha beta. This implies yeah. This implies so what we need to prove? Set of all elements in K which are algebraic over F. This implies set of all elements in K which are algebraic over F forms subfield of K. Implies done. Is this clear or not? Jennifer, is this clear or not?
Okay, sir.
Muthukumar, is this clear or not?
It is okay.
Okay.
Clear.
Okay. Let's go ahead. Now, third question. Where Q is field of rational numbers and fourth root 2 is a real fourth root of 2. Is here. 2. Let A denote the number of field automorphism K to K. A is equals to number of field automorphism K to K. B denote the number of field homomorphism K to C. B denote number of field homomorphism K to C. Determine A equals to 2, A equals to 4, B equals to 2, B equals to 4. Tell me, is this true or what? Okay. So first try to understand the statement. So K is the field which is the smallest field containing Q and fourth root of 2. So Q is a field of rational number where fourth root 2 is the real fourth root of. A is a number of field automorphism from K to K. What is the automorphism?
Isomorphism from K to K.
Yeah, it's same to same. Yeah. Ravi Shankar, what is the definition of field homomorphism?
Yes, sir.
What is the definition of field homomorphism?
Field homomorphism. Sir, exact I don't.
Jennifer, what is the definition of field homomorphism?
F of x y is equal to f of x into f of.
Okay, and
Then f mapping from
what is the definition of ring homomorphism?
mapping should be
Muthukumar, what is the definition of field homomorphism?
F of A plus B equal to F of A plus F of B. F of AB equal to F of A into F of B. F of 1 equal to 1.
Yeah, this is ring homomorphism. Do you need any condition for field homomorphism?
So same thing.
Okay. So there is one restriction which your instructor put, that field homomorphism should preserve the base field. So base should go to base, Q should go to Q. Means restricted to Q, it should be identity map. Are you getting my point? Like here base field is Q, so on restriction to Q, it should be identity map. This is assumed by your instructor. Even from Q to Q, there is no other homomorphism than means non-zero homomorphism, like from Q to Q, except the identity one. You can prove this fact. So this is not a worry. So Muthukumar gave a definition of a field automorphism. So now the question says, determine A and B. What are number of field automorphism from K to K? So how you will tackle such kind of questions? Okay, just to determine number automorphism from K to K. How you will determine, do such kind of questions? Here K is equals to fourth root of 2. Q adjoined with fourth root of 2. This is the field. This is the field. So how you will do such kind of questions?
Sir, can you answer the question?
Yeah. You can see. Anyone have any idea? You can share with me, otherwise I will solve this one. What is the conditions on element of this field K, where it can go under field homomorphism? You have proved something special about field homomorphism, where the like this is just a the field, the Q adjoint 4 through 2 is just a field Qx modulo x to the power 4 minus 2. So now what you can say, where the element of this field can go, where the fourth root of 2 can go, you can say something about that. Okay, let me ask you first. You are not even clear in. Have you done this field theory classes? Because I guess this was done in your class. Instructor did many things in your course, but you don't even know definitions. Okay. Let me tell you. So
We
fx
start with f of 1 equal to 1.
x to the power 4 minus 2. Okay, let me start with this one. X to the power 4 minus 2, this polynomial. So K is basically this field, right? Qx mod x to the power 4 minus 2. Under the isomorphism I gave above in first part or second part, A or B part, something in our question. So what? So now basically, what is this field? What are the roots of this polynomial? So what are roots of f? These are precisely fourth root of 2, which is a real number. Then you can just multiply them by fourth primitive root, means fourth root of unity multiplied with this element, right? What are the fourth one? 1 minus 1. So minus fourth root of I should write clearly, minus fourth root of 2 iota fourth root of 2 minus of iota fourth root of 2. So yeah, so now he is saying the adjoint field he is obtaining is a real field. He is right here in the question, this one is a real fourth root. So now if this field is, he obtained Q, he adjoined Q to some real fourth root. So this field is some subfield of real number. So now see, now you can see where, who erased this one? I write this element also here, fourth root of 2. Okay, so now see, this 2 element is not in K, does not belong to K, right? So now any automorphism sigma from K to K, then what is the choice where the fourth root 2 can go, where it can go? This is my question to you.
So to real number only, no? मतलब
अरे भाई कोडोमेन ही रियल नंबर है तो जाएगा तो रियल नंबर में, बट जाएगा कहाँ, where it should go? Okay,
so to two.
Muthukumar, do you have any idea?
Fourth root of 2 plus ideal generated by x power 4 minus 2.
Why this?
Okay.
Right, this is means just you are saying that identity map. Is there any other map? How you will say this? You have precisely done this statement. Let me prove this one if you've not done, otherwise state it. Proposition. I hope this is done in your class. Alpha belongs to K is root of some polynomial, say fx belongs to k over f, this extension fx belongs to fx, then and phi mapping k to k is a field homomorphism, then phi alpha is also root of fx. Means the image element can go only if alpha is root of some polynomial, then it can go only to other root of that polynomial. That's what I'm saying. So how we will prove such kind of statement? So suppose, okay, alpha belong to root of fx. Let fx be xn plus an minus 1, xn minus 1 plus a naught. This is the minimal polynomial for alpha, suppose. Now, where this phi of, okay, okay. So how you will say? This field under this homomorphism fx to fx, this one goes where it goes. You can see alpha satisfies this one. We know f of alpha is equals to 0. That means alpha to the power n plus an minus 1, alpha to the power n minus 1 plus so on, a naught is 0. So what? Apply phi to this one. This implies phi alpha to the power n plus phi of an minus 1 alpha n minus 1 plus phi of a naught 0. So what? This implies phi alpha to the power n, but see, this is phi of an minus 1, phi of alpha to the power n minus 1. Let me write this, phi of a naught plus 0. Now see, these are an minus 1, a naught, a naught, a2, an minus 1. All these are element of f, but under field homomorphism, f restricted to phi is identity. But since phi restricted to f is equals to identity, that means phi of ai is equals to ai. So that means phi alpha to the power n plus an minus 1, phi alpha to the power n minus 1 plus so on plus phi of a naught is equals to 0. This implies phi of alpha is root of polynomial x to the power n plus an minus 1 x to the power n minus 1 plus so on plus a naught, which is same as fx. So I prove. So what I prove? So we are done.
If alpha is the root of a polynomial, then pi of alpha is also a root of the polynomial.
Okay. So yeah, apply this to here. How you will apply? These two are not elements. Iota 4th root 2 and minus iota 4th root 2 are not element in K. So now you are only these two elements in K. These two elements are in K. So one is the choice that 4th root 2 can go 4th root 2, and on Q it should be identity, right? Because this is a field homomorphism. And other choice is 4th root 2 can go to minus 4th root 2, right? Okay. You are getting or not? K to K number of field automorphism we have to determine. You are getting or not? Tell me. Otherwise, I will explain again if you are not getting. Otherwise, I will assume that you are getting. Muthu Kumar, you are getting or not?
Yes, we are getting. We will go through and then I will go.
Okay. Jennifer, are you getting?
Yes.
Okay, so let me just quickly go again through this. What is the idea? I proved by this proposition that if alpha is root of some polynomial, then under any field homomorphism, phi alpha is this homomorphism can send only to image phi to root of that polynomial. Means this field homomorphism can do nothing but just permutation of the roots. Can permute only roots. So if alpha is root, then phi alpha is also root of the same polynomial I proved. So now here the polynomial is x to the power 4 minus 2. So now its root, fourth root 2 is its root, right? So k is just a q adjoint with fourth root 2. Now fourth root 2 is a root of this x to the power 4 minus 2, and this is a real root. He is saying that k is just q fourth root 2 adjoined by real fourth root 2. So these are two real fourth root 2. So if k is the field obtained by q fourth root adjoining q with fourth root 2, then minus fourth root 2 is also there. So now under any field what are the choices of field homomorphism here? So now the question comes with us is, okay, what are field possible field automorphism? Okay, this is the question. So k is equals to q fourth root 2 to q fourth root 2. Now since any field automorphism phi restricted to q should be identity. So let phi is such field automorphism, then what? Phi restricted to q should be identity. So now only need to define for fourth root of 2. Only need to define fourth root of 2. So what are, by our proposition, possible choices are fourth root 2 goes to fourth root 2 and minus fourth root 2 goes to minus fourth root 2. This is one choice. Let's assume this one phi 1 and fourth root 2 can go to minus fourth root 2, minus fourth root 2 and minus fourth root 2 can go to fourth root 2. This is phi 2. So these are the only two choices. Can check. Both are injective and surjective by definition, and you need only check that this is a field homomorphism. Field homomorphism is obvious. You just need to check ring homomorphism because by definition I fixed the Q. Can check that this is field homomorphism, and by the way we define, it is bijective. This implies number of automorphism from k to k equals to, so yeah, So we have proved that number of field automorphism from K to K A equals 2. Now we have to find number of field homomorphism from K. Is this clear or not? First tell me, is this clear or not? If not, then ask me your doubts. Tell me. Unmute yourself and tell me, is this clear or not?
Is clear.
Okay. Ravi Shankar, is this clear or not?
जी सर समझ आया थोड़ा थोड़ा.
Okay. Now he is asking us what number of field homomorphism from K to C. Now, if field homomorphism, then root can go to only other root of this polynomial. But now see, now the field homomorphism to C we have to define, not to K. So all roots are there in C. Here I exclude these two possibilities, right? Here I said that iota 4 through 2 and minus iota 4 through 2 are not there. But now we have all roots are there. So what are the all possible field homomorphisms? To find all possible field homomorphism from K to C. K is just Q 4 through 2. Right. Now see, I can send this 4 through 2 to 4 through 2. This will give me identity homomorphism. I can send this to minus 4 through 2. I can send this to iota 4 through 2. I can send this to minus iota 4 through 2, right? These are the only possible choices. And all these are element in C. Here I include these other two choices also because they are also element of C. So only possible choices are these, and you can check that all these determined field homomorphism, we just fix the Q and 4 through 2 send this, then all the other element choices are automatically determined. Are you getting or not?
So the value of B equal to 4. Okay. We are
Yeah.
getting it.
Yeah. This will give
Sir, is this the only possible field homo here with Q for respect?
I prove a proposition. What I prove? Tell me.
Yes, 1 second.
What I prove? Tell me. I prove a proposition under field homomorphism where an element can go. If an polynomial f satisfies, if alpha is root of some polynomial f, then under this field homomorphism, phi alpha should also be root of the same polynomial. Now,
Yes,
since
sir.
4 root 2 is root of the x to the power 4 minus 2, and this is minimal polynomial for 4 root 2. So only choices for its image under any field homomorphism are only these 4 elements. Under C, C is algebraically closed. All these elements are in C, so all choices are possible in this case. So that's why we will get four field homomorphism. So this implies okay. So I hope this is clear. If not, ask. Is this clear or not?
Yeah. Yes, sir. Clear.
Muthukumar, is this clear?
Yes.
Jennifer, is this clear? Okay. So let's do some other things. This assignment is done. So we have 13 minutes remaining. Let's take some problem from somewhere and solve it. So I am taking your previous year assignment questions. Okay. So here is the problem. Let me write. So choose all correct statements is the problem. Fourth question. This is the first option. Every subfield of the field C contains Q. Is this true or not? If true, give me proof. If not, give me counter example. So tell me, what is justification? Jennifer, is this true or not?
Sir, it is true.
Okay. How you will prove this?
Sir, there is always a rational number in the neighborhood of an irrational.
How you will come to that idea? Where irrational comes in picture? I just ask you that is every subfield of complex number contains Q or not? I don't ask you any analysis, how much denseness or this. This is analysis business. We are doing algebra here. Muthukumar,
Q contains no proper subfield.
okay. So what? Is this statement true or not? If yes, give me some idea. If not, give me counter example.
Okay, it is true.
Why? Is Z mod NZ is a subfield of complex number? Suppose Z mod PZ. Can you give
Is it
some?
true?
Yeah. Tell me. Yes or no?
Z mod P Z is a field when P is a prime number.
Yeah. So I am asking, is this subfield of complex number? If this is subfield of complex number, then this statement is false, right? This does not contain Q. So is this true?
Sir, which example you took?
I didn't took any example. I'm just giving you idea, or is this true or not? What you can think. I am asking about field, finite field, Z mod PZ. Is this subfield of C? Oh God. How you are doing this course? You don't even know basic things. Question. Is subfield of C. So how you will do this? Is this subfield of C? For subfield, you need to show some injection from here to here. You need to some injection show to here. Is this exist or not? You need to show. If there exists some injection, then it is a ring homomorphism. So one should go to one. So what can it be injection? P minus one should be go one, then two bar should go to two bar should go to 2, and so on, so on, so on. P minus 1 should go to P minus 1. Then where P will go? P minus 1 should go to P. Now what you can do? Phi of P minus 1 plus p minus 1, where it should go? It should be phi of p minus 1 plus phi of p minus 1, which is 2p minus 2. But what is this? P minus 1 plus p minus 1. Phi of 2p minus 2. What is 2p minus 2?
P minus 2.
This is p minus 2. So this is p minus 2. Is 2p minus 2 same as 2 minus p minus 2 in C? For any prime p. Is this? Tell me yes or no at least.
No, sir.
Yeah. So that's why there cannot be such injection. This implies that does not exist. This implies Q. What I'm proving. This implies Z mod PZ is not subfield of Q or C. Okay. So now we prove that this is not subfield of C. So now is this statement true or not? Every subfield of field C contains Q. At least one kind of examples we counter out. Like we claim that finite field are not subfield of rational numbers or complex numbers. So if they are subfield, then this will be false, right? Then we will give that this is not subfield. So is this statement true or not? How will prove this? Suppose, okay, justification. Justification. Okay, so if suppose L is any subfield of C, then what? Agar L को if L is any subfield, this implies 1 must belongs to L, right? Agreed or not?
Yes, sir. Agreed.
And minus 1 also belongs to there. Inverse of 1 should be there, right?
Yeah,
Additive
yeah.
inverse.
Yes, sir.
So if 1 is there, then 1 plus 1 plus 1, any number of n number of times is also in L, right?
Yes, sir. Closed.
Yeah. Similarly, minus 1 plus minus 1 plus minus 1 n times, this should be also there, right?
Yes, sir.
This implies Z should be contained in L, right?
Yes, sir.
Now, if Z is contained in L and L is a field, so every non-zero element of Z should have inverse in L, right?
Yes.
This implies what? Q is contained in L. This implies so is this clear or not? Tell me.
Yes, sir. So through counter example.
Yeah.
Taken yes.
Yeah.
L is any subfield of C. So 1 in L and minus 1 in L, therefore you have proved both positive and negative integers, including 0 or in L.
Yeah. So if so all are there. So if L is a field, so all multiplicative inverse should be there on non-zero element. So Q should be in L.
So you have taken the inclusion map. What can you say about the inclusion map? Is it to L?
Yeah, like it is just one goes to one. Okay, what is this inclusion? This inclusion is just one of Z goes to one
The
of,
same object.
yeah, one of Z. Then it is defined unique. Now by same argument, since every non-zero element in Z should have inverse in L, so Q should contain in L because L is a field. So this implies every subfield of L of C contains Q. So is this clear or not?
So every non-zero element in Z has a multiplicative inverse in L.
In L, yeah. And Q is precisely the all non-zero element of Z has inverse. This is the smallest field, right? This was done in your localization section in your course. So we are done.
Sir, here we have taken multiplicative inverse, no? But
Yeah.
for closeness proving, we took additive inverse, no? Like 1 plus 1 plus 1.
So what?
So,
1 plus 1 says that 2 is there. Multiplicative closeness says that since L is filled and 2 is in L, so 1 by 2 should be in L also. So 1 by 2 is there. So all rationals are there. In similar way, you can argue. Rational are P by Q form, right? P and Q are in integer
yes,
Q non-zero. So that's what I proved here.
yes, sir. Yes, sir, correct.
Okay. Jennifer, is this clear or not?
Yes.
Muthukumar, is this clear?
Yes.
Okay. We can go ahead. Okay. The degree of square root n over q is 2 for every positive integer n. B option is saying the degree square root n over q is 2 for every positive integer n. So is this true or not? Muthukumar, is this true or not?
Because the polynomial x squared minus n.
Yeah. Is this the minimal polynomial always for any n?
Because any first degree polynomial.
What about n equals to 4?
First
Take n
degree
equals to 4.
polynomial. First degree polynomial in Q
Oh, yeah.
over Q
Yeah.
will not satisfied by root n.
Why? Take n equals to 4. Root n will be 2. So what? X minus 2 satisfies, right?
You have written for every positive integer n.
Yeah, this is the saying the statement. The degree root n over q is 2 for every positive integer n. He is saying this.
Yes.
So I am giving you an integer for which it is not. Take n equals to 4.
If I take n is equal to 2.
Okay, for every he is saying for n equals to 2 you are fine. This is 2 degree x square minus 2 you need it. But he is saying for every positive integer n. So let's take positive integer 4. If you are saying some statement is true for all integers, then it should be true for every integer. But
Yes.
I am claiming that this is not true for integer 4. So take n equals to 4. Square root 4 is 2. So x minus 2 is a minimal polynomial. So its degree is 1, right? So this is,
so the statement is false.
yeah, this is
For
false.
every positive integer n, that is the point to be noted.
Take n equals to 4. Then degree of root n is equals to 1. So next option. Let's finish this question, then we will end this session. The degree of root 2 plus root 3 over q is 2. is 2. Is this true or not?
This is false.
Why?
This is the root 2 plus root 3 is of degree 4.
Yeah. Correct. This is the diagram justification I gave you. These are all 2-degree extension. These are independent of each other. So this is false statement. And the last part is the degree of root 2 plus root 3 over q root 2 is 2. The degree of root 2 plus root 3. Okay, so this is true statement. Justification. What is justification for this? Over q root 2, minimal polynomial for root 2 plus root 3. This is just okay. So by this one, by C, okay, the degree of root 2 plus root 3 belongs to q root 2 comma root 3 and q root 3 over q root 2. This degree extension is less than or equals to q root 3 over q, which is equals to 2. So this is less than 2, and you can prove that this is 2. So q root 3 over q is 2. This implies q root 3 over q root 2 is less than or equals to 2. But since root 3 does not belongs to q root 2, this implies degree of extension q root 3 over q root 2 should be greater than or equals to. This implies q root 3 over q root 2 is equals to 2. So this is 2. So is this clear or not? We are out of time also. So just confirm, is this clear or not?
It is clear.
Okay, thanks. So with this, we will end this session here. If you want to say something, comment something, or suggest something, you can.
Hello, sir.
Yeah.
Sir, I missed the initial 1 hour. So can you just recapitulate what you did in the